Okay, so here's two just simple bits of data about the orbit of Earth and the orbit of Mars. So the Earth takes 365.256 days. What's that extra 0.25?
Well, that's going to become a leap year.
Yeah,
Every 4 years.
that becomes a leap year. Yeah, and then it's still not exactly 0.25, so you do have to correct.
Yeah.
Do you know when that correction happens?
It's leap seconds.
No, that's going to be a different phenomenon. So the leap years are not always every 4 years.
And they're not. But it's either there have to be multiple of 4, but not 100. Or I think 400 also works.
Right, so you have some corrections in leap years.
So like 2100 is not going to be a leap year.
Right, but 2000 was.
Yeah.
Mars has an orbit of 680. So it takes 687.0 Earth days. So the way we measure a day, and it has a semi-major axis of 227.9 million kilometers. So Earth, Mars is a little bit farther away from Earth.
Yeah.
And it's going a little bit slower. But Kepler, have you ever heard the name Kepler?
Yeah.
Yeah, the astronomer.
The astronomer calculated that for planets and actually other bodies orbiting around something, that the time it takes to orbit squared divided by the radius cubed is constant. It's a little bit more complicated than this because the orbits aren't quite circles, but I'm doing a little bit of an approximation for now. So he noticed that the time squared divided by the radius cubed was constant. So we're going to do that calculation real quick.
Alright.
So for Earth, this is 365.256 squared. So 365.256. Is my phone in the picture?
It is.
Times 365.256. So that's 133, call it 412, 411.9. And then 149.6 cubed. 0.6. So I get on the bottom 3,348,000. Oh,
72.
call it. So I'm gonna do on the top, I'm gonna do the thousands divided by the millions. So I'm gonna do 133.4 divided by 3.348. Okay, because I'm just gonna like multiply the bottom and top by 10 because we're supposed to be getting something that's constant. So 133.4 divided by 3.348, and I get sort of
0.84.
39.84. Okay, so Earth I get 39.84. Alright, so remember we're doing thousands divided by millions.
Alright.
Okay, so let's do the same calculation for Mars now.
Alright.
So yeah.
So 687 squared.
Alright, do you wanna type that in? 687 squared?
71,969.
471.969 over 227.9
Cube.
So go ahead and do that.
Oops. Equals 11,836,763.6.
11,836,763. So I said we're going to do thousands divided by millions. So 471.969. Divided by 11.836. So 471.969. Oops, I did 999. Doesn't matter. divided by
It'll be
11.
close enough.
836. Then I get 39.887.
So it's pretty close.
Yeah, it's an interesting law. So this is one of Kepler has 3 laws about planetary motion, but this is the third one, and it helps you understand how the orbital time relates to the radius. That's pretty neat. Pretty neat. And then we can see, just looking at Earth and Mars, that it does seem to obey Kepler's law. Actually, I think that Mars actually helped Kepler understand the planets a little bit better, because Kepler was trying to. I think at the time Kepler thought the orbits were circles, and they had good enough observations of not Venus, but good enough observations of Mars that he could see that it wasn't a circle.
That wasn't the same, didn't look the same in the telescope through the year.
No, actually, funny enough, that's what we're going to do next. What Mars looks like throughout the year. But he could see through the telescope when he did his calculations that Mars's orbit wasn't a perfect circle. So that helped him develop the laws. So actually studying Mars has been a very important piece of astronomy for how humans have understood astronomy. But anyway, we're gonna take a look on the computer at the orbit of Mars.
All right.
All right.
Okay, here we go.